Welcome to Fundamentals of Distillation Operation. This video will guide you through a virtual distillation plant where crude oil is separated into several refined products. The basics of distillation are explained by covering each component in the plant step by step. After this introduction, we'll look inside a distillation tower, view how separation is established, see how gas and liquid flow through the tower, and discuss common issues resulting from incorrect operation or damaged equipment. Let's remove all components surrounding the distillation column. Distillation is the most common separation technology used in petroleum refineries. The separation of substances is accomplished by making use of the differences in volatility. The liquid mixture is separated into fractions through partial vaporization and the recovery of the vapors and residue. The distillation towers have liquid outlets at intervals up the column which allow for the withdrawal of fractions that have a specific boiling point or boiling range. The lightest products exit from the top of the column. The heaviest products exit from the bottom. Products exiting from the top have a lower boiling point than those exiting from the bottom. The process is operated at a continuous steady state. New feed is constantly added as products are withdrawn. The feed is preheated, in this case by a furnace. The heat vaporizes the volatile components, and the vapor and liquid are fed into the column. The liquids will pass down the column into the stripping section, while hot vapors pass up the column, which is referred to as the rectifying section. Inside the column, a series of trays force contact between the vapor and the liquid. To maintain the appropriate temperature in the column, the necessary heat is supplied by a furnace reboiler. Part of the bottom product is pumped into a furnace and fed back into the column. Reboilers generate the vapor to drive the fractional distillation, and therefore proper reboiler operation is vital to effective distillation. This picture shows how the furnaces and the column we discussed are represented in a diagram. Steam stripping may be required for compounds that will decompose at sustained high temperatures. Because normal distillation will not work effectively, steam is added. The addition of superheated stripping steam lowers the hydrocarbon partial pressure in the tower. This lowers the boiling point of the compound. Therefore, steam stripping will allow a fraction to evaporate at a lower temperature, avoiding the decomposition resulting from normal furnace reboiler operation. Here we see a high-pressure steam stripping sparger that is used to distribute the steam into the column. The pipes have small holes acting as orifices to maintain the appropriate pressure. It is important that the superheated steam is completely dry and doesn't contain any condensed wet elements. By routing the steam through a knockout drum, the wet steam can be collected as it condenses in the drum. The dry steam can now safely be added to the column. Lighter products exiting from the top of the column are recovered by letting them cool in the overhead section. Vapors are condensed into a liquid. In this case, the heat exchange is established by air cooling using a series of fans. The hot product moves through a series of pipes while these fans blow air from the bottom. The latent heat is given up by the product and will transfer to the air. Gaseous substances will condense to their liquid state, and the liquid is then recovered into a reflux drum. The liquid is further allowed to cool off in the reflux drum. At the bottom of the reflux drum, a boot is collecting water. As water is heavier than oil, it will sink to the bottom of the reflux drum and can be purged from the system. Part of the condensed portion of the lighter liquid is pumped back into the column. This reflux achieves a more complete separation of products. Inside the tower, the downflowing reflux liquid provides cooling and condensation of the upflowing vapors. Reflux improves the separation process and therefore the quality of the product and efficiency of the tower. In general, the more reflux provided, the better the separation of lower boiling materials from higher boiling materials. However, the amount of reflux that can be used is limited. The process of separation is driven by the liquid-vapor interaction, and if this is out of balance, efficiency can be lost. Further, since reflux introduces liquid that has been allowed to cool down, the reboiler needs to work harder to compensate. In other words, increasing reflux can increase costs of operation. Here we see another thing that can happen when excessive reflux is used. The spray headers introduce so much liquid that it starts to form a barrier for the vapor flow. The vapors can't escape to the top and flooding results. In some units, undesired elements could make their way to the side draw. For example, the H2S shown here should escape in its gaseous state from the top of the tower. From there, it would be processed in the gas recovery unit and ultimately in a sulfur plant. However, in the situation where the flow of vapor is blocked, the elements could show up in the side draws. This is highly undesirable and should be avoided. The H2S in this case is used as an example. Each feed is different and will have unique properties to consider. Water collected at the reflux drum needs to be properly drained. If it is not properly removed from the pump-around system, the cold water entering back into the column can have disastrous results. Cold water will expand about 1,600 times when making contact with hot oil. The expansion will create an enormous pressure increase that can severely damage the tower internals. An intermediate reflux or pump-around system is added to further increase the efficiency of the distillation process. Hot liquid is withdrawn from the column and allowed to cool via a system of heat exchangers, after which it is pumped back into the column. Like the reflux pump-around in the overhead section, the intermediate reflux cools the upflowing vapors as the cooler liquid flows down. This smooths the overall temperature profile and therefore improves the separation of materials. The fractional distillation process allows for withdrawing specific products besides the overhead and bottom products. At particular elevations, liquid is withdrawn from the column and fed into a stripper. The temperature of the product in the stripper is maintained at a specific temperature, so that the components that have a lower boiling temperature are fed back into the distillation column. The liquid collected at the bottom is considered the desired product. Here we see the addition of the stripper, supporting pumps, and heat exchanger. In this application, the stripper shares the side draw line with the intermediate reflux system we discussed earlier. The same principle applies to the second stripper in this particular system. Let's review what we discussed. Central to the plant is a distillation tower in which oil is separated into refined products. The separation is established by preheating feed and reboiling liquid, resulting in vaporizing of volatile components. The overhead section condenses the vapors exiting from the top of the column and collects it in the reflux. Water is drained from the reflux drum. Part of the overhead product is fed back into the column as reflux, providing cooling of the rising vapors to increase the effectiveness of the distillation process. Intermediate reflux further smooths the temperature profile by pumping liquid around, returning at about half the height of the column. Strippers are added by withdrawing products at specific positions in the column to recover particular products. Now we've examined the supporting equipment for a distillation tower. Let's take a look inside the column to see how liquid and vapors interact and how separation is accomplished. Here we see a set of trays positioned at about 24-inch intervals. Each tray has a number of bubble caps. The vertical distance between the trays depends on the composition of the feed and the desired separation of components. When the boiling points of the components are relatively close, the trays will be positioned closer to each other. A larger temperature differential in boiling points is better served with a tower that has a larger gap between the trays. Usually, trays will have a manway that can be removed and bolted back into place. The manway allows for personnel to climb through the tower when the system is out of operation for inspection, cleaning, or repairs. On one side of the tray, a weir is positioned right above the downcomer. Each tray is oriented at a 180-degree angle from the trays above and below, alternating the position of the downcomer from left to right as we move from tray to tray. The liquid on the trays completely submerges the bubble caps on the trays. As the liquid is heated to the point of partial vaporization, the surface is quite dynamic. The weir on the tray is designed to maintain the appropriate liquid level and therefore the hold-up time on the tray. Additional liquid will flow over the weir and accumulate between the downcomer, the shell, and the tray below. Here the process will repeat itself, thus creating a downflow of the liquid. Components that vaporized at lower boiling temperatures create an upflow of vapor. During normal operation, the vapors cannot enter the downcomer area as the liquid properly seals the passage. The vapors are forced through the bubble caps on the tray above. Therefore, as the bubble caps are submerged in the liquid, the interaction between vapor and liquid is maximized. Bubble cap trays are particularly efficient for accomplishing the interaction. Here we see a cross-section view of a bubble cap. The pressure from the vapor upflow prevents the liquid from entering the bubble cap. The vapor enters the riser pipe, moves down inside the cap, and enters the liquid through the bottom and the cutout slots in the bubble cap. Effectiveness of the distillation process greatly depends on proper reboiler operation. If, for example, the reboiler does not provide sufficient heat, there will not be enough vapor rate. If the rate is too low for the design of the tray, the vapor can't force its way through the liquid, lowering the liquid level. The fluid could even enter the riser pipe and trickle down to the tray below. This is referred to as weeping. Excessive weeping can result in dumping, in which all liquid will move down to the base of the column. The steady state will be compromised, and it may be necessary to restart the process. Weeping can be detected by a sharp pressure drop in the column in combination with reduced efficiency. When liquid levels get too low, an undesired passage to the downcomer area can result. Vapors will find the way of least resistance and will move up through the downcomer area instead of through the bubble caps. No interaction between the liquid and the vapors will be established, and the distillation process will be seriously compromised. The interaction between the liquid and the vapors is vital to proper distillation. When the hot vapor makes its way through the liquid, heat is transferred to the liquid. Some of the vapor will condense as a result and is added as liquid to the tray. At the same time, because of the heat transfer, the liquid will boil and generate more vapors. The continuous contact between vapor and liquid on each tray brings out the separation between components with lower and higher boiling points. Other causes of vapor entering the downcomer area include situations where the downcomer is damaged or not properly sized. In all these cases, the vapor is allowed to escape because the liquid is not creating a proper seal with the downcomer. If the weir is damaged or the tray is not level, the liquid level may not be properly maintained. Again, no contact between liquid and vapor is established as the vapor moves through the downcomer area. On the other hand, if the reboiler provides too much heat, the vapor rate will increase and create so much pressure that the liquid level on the tray will rise and flood the trays. As the liquid level rises, more liquid will flow over the weir to the tray below. The increase in liquid level will also back up the liquid in the downcomer area, increasing liquid holdup from the tray above. Flooding can be detected by an increase in the differential pressure and a significant loss of efficiency. Proper reboiler operation will prevent weeping and flooding of the trays. Temperatures and differential pressures need to be monitored to ensure operation within the design parameters. In addition, infrared scans can help in determining the cause of improper operation. The scan will reveal differences in density and can therefore be used to verify correct operation or identify problem areas. Other tray designs typically include the basic components we discussed. It will have a weir to maintain the appropriate liquid level on the tray. It will also have a downcomer, and it will have a mechanism for vapors to enter and make contact with the fluid. The method we discussed was using bubble caps. Sieve trays have the simplest design by just having holes for the vapor to enter. In valve trays, the perforations in the tray are covered by caps. The rising vapors will lift the caps, creating a way for the vapors to enter the liquid. The caps direct the flow horizontally into the liquid. Compared to sieve trays, valve trays provide better gas-liquid interaction. The choice of design depends on the type of operation and the required pressure drop between the trays. However, because of their efficiency, bubble cap trays are preferred in many applications. The tray designs discussed are part of staged contact columns. The contact between liquid and vapor occurs in stages at each tray. A continuous contact column doesn't use trays, but a packing material to allow for contact throughout a complete section. The packing provides a large area for contact, while increasing efficiency of the separation process for the same column height. Therefore, packed columns can be designed to be shorter to achieve the same result as trade columns. When a side withdrawal of liquid is required, the tray designs may be slightly different. In the introduction, we saw a few examples, like the draw for the intermediate reflux and the strippers. This cross-section view of the column shows one possible design. In this tray, fluid will drop down to the tray below in the middle of the tray. On both sides of the downcomers on the tray below, a weir is present to maintain the appropriate liquid level. The left side of this tray continues the liquid downflow. On the right-hand side, the tray level drops to create a larger holdup area from which the liquid can be pumped out to the appropriate equipment. Vortex breakers are devices that can be found at the liquid outlets. They are designed to eliminate gas carry-under in the liquid stream. The vortex breaker will stop the swirling of the liquid. A vortex-shaped swirl has the tendency to suck vapor into the liquid stream that could cause pumping problems. As we discussed before, tray damage can have a great impact on the separation process. When the liquid-vapor interaction is compromised, the efficiency of the fractionation will decrease or, in the worst circumstances, be lost. Let's look in further detail at some situations where trays can become impaired. We talked about the importance of purging water from the reflux and dry steam before introducing it to the column. Failing to do so will create a large pressure increase when the cold water and hot oil make contact. The trays can get damaged at their weakest points, the points where the different pieces are bolted together. The pieces can separate and lift out of position. As illustrated here, the liquid level is lost and the vapors are allowed to escape without making contact with the liquid. In the situation where the liquid level is very low, the temperature will rise because the liquid vapor rate is out of balance. Overheating of the oil can result in coking, leaving behind a solid residue that could plug the trays. If the liquid level is completely lost and the tray is running dry, the temperature of the internals itself will increase. The liquid acts as a heat sink to the heat the vapor is providing, and when lost, the trays can warp and bend out of shape because of the excessive heat. Here we see the liquid being drawn, for example, to be used for intermediate reflux or for further separation in a stripper column. If the draw rate is too high, the liquid level can be lost. The resulting damage to the tray will result in less efficient operation even after the draw rate has been adjusted to the proper set point. When the liquid level at the bottom of the distillation tower is too high, stripping steam may be introduced below the surface of the liquid. This will result in condensing of the steam and wild turbulence of the liquid. The liquid level will lift and has the potential of damaging the trays above. Plugging of the internals causes bad distribution. Plugging can occur in various internals of the system. Let's look again at the coking deposits caused by running liquid level too low. The vapors do not have proper passage anymore. The liquid-vapor interaction will be diminished, and therefore the effectiveness of the operation is reduced. Other causes of plugging of the trays include leaving salt deposits. This is referred to as fouling trays. When the overhead system is running too cool, residue that should have left as vapor from the top of the column is deposited on the trays. Besides the negative effect of the plugging, the metallurgical effects, like corrosion of the reaction between the metal and the salts, should be considered. Metallurgy is outside the scope of this presentation. The negative effects of plugging can potentially be found in the distribution system of the reflux. These distribution headers reintroduce the liquid into the column as uniformly as possible. Plugging of some headers causes a bad dispensation profile. Components of the vapor that should have condensed against the cold reflux are now allowed to pass to a higher level. The temperature profile will not be as smooth as with a properly functioning reflux distribution system. The distillation system, with all its supporting equipment, will operate in a steady state. Increasing or decreasing operational parameters of one component will have an effect on the rest of the system. We've discussed several situations where, If we operate outside the proper limits, internals are being damaged. Operating within the appropriate boundaries gives the operator control over the efficiency of the system and the quality of the end products. We also discussed the effect of reboiler operation on the separation process and the results of adding reflux. This leaves us with the draw rate of the product. What are the results of increasing or decreasing the operational parameters? If the operator chooses to increase the draw rate of a side product, the following will result. As the liquid level on the trays decreases, the liquid-vapor ratio will change. As a result, the temperature will increase. A higher temperature will allow for heavier products to vaporize and make their way to the light ends. So the harder we're pulling product, the hotter the tower gets, the heavier the end product at the overhead will be. This concludes fundamentals of distillation operation. In summary, we've discussed the common components of a fractionation plant. These include the distillation tower, reboiler, overhead condenser, reflux drum, intermediate reflux or pump around system, and strippers to service side draws. We looked at various internals like the trays, bubble caps, spargers, distribution headers, and vortex breakers. Other subjects covered include causes of tray damages and the results thereof, the effect of changing the operation parameters like reboiler temperature and draw rate, causes of plug trays and distribution headers and their symptoms.